Welcome to another episode in computational fluid flow and heat transfer course. In the previous class, if you remember, we derived the governing equation in fluid flow and heat transfer for both viscous and viscid as well as incompressible and compressible flows. We saw those governing phenomena expressed in partial differential equation forms. We also saw that fluid flow and heat transfer computational analysis involve modeling, equation development, discretization, followed by applying boundary conditions and simulation. In today's session, we'll see what simplification methods are available and their scope of application, followed by characterization of partial differential equations, then discretization and the solution techniques, applying boundary layer theories. So these are the remaining topics in our course. Please note that these concepts are meticulous and require a lot of preparation and testing it for first hand for accuracy, as every specific set of problems it will be accuracy and modeling within both source and visual computational codes in industries. Solving governing equation in fluid flow is very important. Partial differentials. You need either simplify using similarity transformation or other relevant techniques, or analyze the partial differentials using discriminants. Simplification from PDEs to binary differential equation involves transforming the equation using similarity variable or geometric symmetries. This reduces governing equation into form of single independent variable, aka only differential equations, with much reduced unknowns. Standard numerical methods use simplified form of governing equation. On the chart, this is important in modeling ring of long hot rod, missile launches, or ship deck heating. Transient term is given by nullity with respect to the spatial temperature gradients are the right hand side. Base thermal diffusivity, isotropic materials, which the ratio of thermal conductivity to density in the specific state. The spatial similarity variable introduced here is radial symmetry in cylindrical or spherical coordinates. Typically cylindrical. Note dimensional transformation here, which enables first order derivative in transient term and second order derivative in the spatial temperature gradient on the right hand side. By introducing the characteristic similarity variable, it's the square root of quotient of I square, which is x squared plus y squared over alpha t, enables comparison of both sides. When you substitute eta and subsequently derive f twice with respect to time and eta, you will arrive at second order ordinary differential equation, which can be integrated twice for a general solution. boundary conditions applied for a specific particular solution. Another similarity variable which can be introduced here in thermal analysis can be temperature differences, such as theta, the most recent temperature minus initial to surface temperature minus initial, as well as incident model meter. For more details on detailed derivatives in this blunt capacitance model, you can see the lecture note on heat transfer. Simplification or ordinary differential transformation techniques have limited applications. The second widely applied technique in CFD is characterization using discriminants. This involves first classifying partial differential types, then discretize in large systems systematically based on partial differential type, and assemble discrete components, followed by second step is validating convergence and stability by performing linear stability analysis. Third step involves simulating fluid flow or transfer and interpret results accurately. Consider given general form of second order governing equation for dependent variable I xy. Sum of highest second the differential equation quotient, then first and then zeros order partial differentials with coefficients A, B, C, D, E, F, and G that might be as a function of X and Y. We have already seen categorizing partial differential equations as parabolic, hyperbolic, and elliptic, and numerical method based on those coefficients. Problems involving partial differential equations can take the following physical form. The first form is equilibrium or closed domain. The second one, with rare appearance in fluid mechanics, is eigenvalue problem. And the third form is margin problems. With the curve yx satisfies the ordinary differential dy by dx equals to static solution partial differential equations, the specified initial and the boundary conditions. Characteristics are the locus of differences along real curves within the solution domain, but the second derivatives are discontinuous. These represent flow conditions such as shock waves in supersonic flows. Matching problems are parabolic, hyperbolic problems, parabolic or hyperbolic, computed by matching both words from the initial data surface while satisfying the boundary conditions from the given initial value or initial boundary values. See the gray area where the problem becomes well posed with the proper use of boundary conditions, hyperbolic, elliptic, and parabolic equations. Let's review the first similarity transformation technique. These transformations enables the following manipulations. First, by eliminating one of the independent variables, one or two. The second, it reduces the governing equation into one dimension and reduces equation complexity and applicable for problems with self-similarity on the layer growth. Sort of similarity. The quartet or five problem types and responding simplification and transformation as listed. First problem type is one-dimensional transient thermal behavior of long bar in XY coordinate system where heat distribution through thickness is uniform and is governed by heat diffusion equation. The similarity scaling involves transforming the left-hand side 1 over tau as a function of right-hand side alpha by x squared. Considering the characteristic length scale of square root of alpha tau in the range of y, the similarity ratio variable eta is fraction of x to square root of 4 alpha tau for all x greater or equal to 0, where constant 4 selected conveniently for resulting the differential equation horizon for simplification. Substituting and subsequently deriving f twice with respect to time and eta yields the second order differential equation of single variable, aka ordinary differential equation. The next step is integrating twice to obtain general solution and applying transformed boundary condition in terms of eta to find a specific particular solution. The second type of transformation problem is dimensional boundary layer partial differential equation, also its equation. Boundary layer equation. It is simplified to a non-linear differential equation, single independent variable, with similarity transformation. The following assumptions are taken into account. First one is a thin boundary layer where boundary thickness delta is much thinner compared to streamwise flow dimension L. That means boundary thickness is much smaller than the length of the flow. The second assumption is streamwise gradients considered negligible compared to all normal gradients. That is, mainstream gradient is much less than gradient in the boundary layer thickness direction. The third assumption is pressure being considered constant across the boundary layer thickness. Therefore, the resulting Navier-Stokes equation is only streamwise momentum equation. And continue. If you want more on similarity, dimensional analysis with the Buckingham pi theorem, you can review or see this course research with my profile. The similarity variable in In this case, eta equals y times the square root of ratio of free stream flow speed, factor of dynamic viscosity, and the stick length at x. Substituting eta in front equation yields stream function, which is important in flow pattern potential determination. Back to our governing equation, which is reduced form. When we derive f phi with respect to time and eta, f now this case is f of eta, yields the second order differential equation of single variable, aka ODE, or ordinary differential equation, which can be integrated twice or solved using system of ordinary differential equation using shooting method. Please refer or not solving precious linear equations in our previous course advanced numerical method with the shooting method. The problem of PDE transformation is redeveloped flow for being steady, visible, uniform shell type flow with no swirl or rotation as described in the slide. This actually is not similarity transformation. Other examples in succession of this presentation. Instead, it relies on assumptions of steady, fully developed laminar flow, views complex Navier-Stokes PDEs to very simple PDEs in single spatial variable, the radial position. Flow is fully developed when the velocity profile are no longer changed along type length or z direction, which eliminates the need for similarity variable that combines distance, time, and the viscosity, resulting in ordinary differential equation by dr of r du z by dr is constant, and d square u by dy square is 0, solved in r dimension. The other simplification or ordinary differential equation transformation problem type is shear driven flow, also known as Couette flow, where the motion of one plate relative to the other drives the flow. Assumptions in this circumstance are steady, fully developed flow, no special flow gradients in z direction and x direction. Pressure along plate motion and dominant x motion. Those assumptions reduce momentum equation to simplified form as seen. And the integrating twice gives us linear velocity by u at y. We already saw the last problem type in the simplification category as we introduced this session. The illustration also include applied convection radiation boundary condition on surface alongside the radial symmetry transformation. Simplified ordinary differential equation systems have limited applications in real-world engineering. Most fluid flow and heat transfer problems are in the form of partial differential equation. For instance, focus specification of initial data boundary conditions is very important in solving a partial differential equation. Rigorous mathematical optimization of partial differential equations help us to ensure solution stability, convergence, and accuracy. Results interpretation of CFD simulation require identifying dominant frequency of understand energy dissipation or flow behavior. If you are unable to uniquely determine the characteristic condition, the initial data are returned along the characteristic. Consider that the problem is reinforced. Subject different types of boundary conditions. In other words, instability refers to the conditions where small perturbations or error grow without bounding over time. Following slide is characterizing partial differential equation. The first wave equation A is equals 1, B is equals 0, C is equals -1 over V squared. This discriminant is delta, which is 0 squared minus 4 times 1 times 1 over V squared. That is 4 over V squared greater than 0. The equation is hyperbolic with positive discriminant that describes wave propagation phenomena. Equation travels at finite speed along the curve. Equation exhibit discontinuities with two realistic hyperbolic problems include modeling sound waves in air or elastic vibration, solid material. This is common in high-speed CFD simulation of sonic airflow, jet, quick equation, finite speed of information propagation. Solution ultimately depends on the initial boundary data. Which P via characteristic. The second problem is heat equation, which has A is equals alpha, B is equals 0, C is equals 0. The discriminant is delta equals 0 squared minus 4 alpha times 0, which is 0 again, with one real characteristic. This fully describe independent diffusion process. vision in one direction. It requires initial conditions throughout the domain and the boundary condition, special boundaries. The solution proceeds by time marching. Initial data with information propagating at infinite speed through the domain at each time step. The third equation, when it's this equation, A is equals 1, B is equals 0, C is equals 1. Discriminants is delta equals 0 square minus 4 times 1 times 1, minus 4 less than 0 inside the quadratic equation. This implies that the equation is under elliptic category that can describe convection diffusion equation. Elliptic problems include calculating the steady state temperature distributions, heated plate, determining a pressure field within a contained incompressible fluid flow, CFD pressure Poisson equation. It requires boundary conditions specified on all boundaries of the domain. The last characteristic equation is A is equal to y, and B is equal to 0, C is equal to 1. The discriminant known to be minus 4 times y. The reason why it's the mixed category is it changes depending on the sign of y. Mixed type problems include modeling airflow over an aircraft wing, speed increase from subsonic elliptic, y is greater than 0, supersonic hyperbolic, y is less than 0. Adaptive numerical algorithms are used to handle this change in mathematical line. Require both initial condition n is equal to 0 and boundary conditions for all times greater than 0 in the spatial domain boundaries. Generally, stability determined by real component of characteristic equation, where positive real components indicate inherent stability. Unstable problems include transition to turbulence, while negative real components indicate stability. Solution characteristics are therefore determined by real characteristic solution associated with wave-like getting solution, hyperbolic behavior, or imaginary characteristic values associated with diffusive or relating solution. The real-world engineering problems are not as few as the ones we used in the above presentation. Governing questions are discretized into large systems in the form of eigenvalue problem, Regent matrix A times vector RIV equals the product of characteristic diagonals, eigenvalue matrix of equal size with coefficients lambda, the right hand side matrix B and vector B. Characteristic value of lambda real with or without imaginary components, the latter of which you will have whenever you end up in the negative values in the square root inside the quadratic equation of coefficient or characteristic discriminant. If lambda max is real and positive, the anticipated flow solution is unstable, just transition to turbulence. See governing for the partial differential equation, the typical problem. If negative, like equation of parabolic diffusion problem, decaying solution being predicted. Flux lambda, on the other hand, comprises oscillatory growth decaying solution depending on values of the real component. So far, we saw three main partial differential equation. Now we'll proceed to discretization. The illustration shows schemes of one-dimensional finite difference, then 2D finite difference, followed by finite element method, the lastly finite volume. Discretization of steady state equation shown on the first row or on the top. And for the unsteady ones in the second row, imagine that the planes flipped towards you as perpendicular to the screen. The x-axis visible, and time is considered as additional third dimension, pointing vertically upward, as seen in the second row or bottom for the one discretization stencils. What is the first components of the finite difference simulation FDM is subfigure I, J, M, and N. It assumes dependent variable exists only at discrete points, also known as nodes. The top represented by J plus 1, while the bottom is J minus 1. The left is represented by I minus 1, and the right is represented by I plus 1, as we did in numerical method class. Finite difference method is suited for simple geometries with benefits of enforcing boundary condition directly at the grid nodes, but has issue of accuracy, less accuracy, and observation inconsistencies as you saw standard diagonal 5-point stencils in list of local and global fluid domain. On the contrary, finite element method, FEM, in K for steady and subfigure O transient, involves the attempts to track these variations. Space with time specific substance molecules instead of fixed quantities. This can offer mesh flexibility, such as unstructured mesh, and the coding simplicity. It can become resource intensive. Related with primitive variables, velocity, pressure, temperature, and sometimes species, in weak conservation forms. The last category in the column of discretization illustration has broadest applicability of all CFD methods for almost every kinds of problems. In control of finite volume discretization, dependent variables exist or analyzed at specified location within or the boundaries of discrete fixed regions called volumes. This method offers consistency of conservation that it ensures exact global and local conservations at discrete level and less memory usage. In other words, finite control volume method is that with all three conservation equations can be expressed as single generalized transport equation. Remember the previous session that it demands more effort and a complex code due to flux variables such as mass, momentum, and energy. Another concept before we begin discretization, therefore, is time marching. It refers to solving independent ordinary or partial differential equations by advancing solution step by step from initial time to later times. Typically using finite difference approximation time derivatives. We have already addressed one of time marching technique by continuously updating coefficient matrix in the right hand side every calculation and substituting the former values in left hand side with the next. We employ the Crank-Nicolson method to do so. And discretizing governing equation involving transient terms, the unsteady phenomena in the current or future conditions of temperature or pressure at n+1 approximated from the previous, as in the illustration from 1 to 2, using technique called time march. Finite difference method. The recall steady heat equation involving partial differential equation discretized using 5-point formula. Recall the Crank-Nicolson scheme in the other YouTube video. In the case which the governing equation for unsteady one-dimensional heat diffusion considered with no source term. This partial differential equation is discretized using Crank-Nicolson method, where semi-implicit scheme that averages partial derivatives at time steps n and n+1. Another discretization technique is when you track temperature of finite element with conductivity K in 2D space with non-conservative or weak form of thermal diffusion of fluid element J over spatial domain omega. The equation discretized using finite element and approximated by finite dimensional space spanned by base of function phi I. Now comes finite volume method, which is our main focus. Don't get confused by varieties of conservation equations, because each form, whether be weak or conservative form, serve their own purposes depending on relevant type of problem and the corresponding discretization and the solution approaches. This conservative form is versatile, which gives continuity when flux variable phi is 1 and the momentum if our flux variable is u, while phi can take other scalars as well, such as combined heat terms, heat flux terms like enthalpy, viscous dissipation, heat flux, but such energy representation requires careful formulation, as we did during formulation of governing equation. Consider one-dimensional steady Gaussian diffusion equation. This is scalar phi in generic form. Rate of change or temporal change at left-hand side plus net change of momentum, which is difference of convection and diffusion equals source. Here, the right-hand side, P and N are adjacent bilateral boxes for control volumes, and the F is an interface. The distance between these interfaces and respective cell centers given by DFB and DFN. Derivatives approximation. Finite volume involves integral over control volume dp and applying divergence theorem or Gauss theorem for control volume T. The sum of convection and diffusion equals source, where gamma is diffusion coefficient. Then the same central interpolation is used, which is second order accuracy to evaluate convective fluxes divided by being segments between centers and diffusing flux approximated by using a ratio of finite differences. Fluxes at center N and P corresponding distance. In contrast, first order upwind accuracy checks maximum of the flux, the upstream fluxes from either sides of phase based on upstream cell flow value depending on flow direction. Similarly, we see two-dimensional diffusion fluxes, cell-centered and vortex boundaries. Pure diffusion can also be discretized using finite volume method, cell-centered scheme, and upwind in 2D with neighbors, east-west, north-south, vertical internal phase between P and E with the spacing X. So the control volume and the inspiration here is rectangular, with central spacing between neighbors are delta X and Y's with the corresponding subscripts. So between P and E, spacing X, E, the diffusion flux, which is the dot product of flow gradient and the normal vector in the east estimated by finite difference, which is a quotient of value differences between east and P divided by corresponding center distance. The first diffusion factor determined by multiplying the diffusion coefficient by ratio of corresponding area to center distance. Note here that we skipped interpolation because we are not dealing with convective flux. Just mentioned in the reference to all reverse direction. Here is the table with 3 columns headers. Respond to central difference derivative approximation, which is flux CD C dot normal vector estimated as function of the difference in the x or y. And phase diffusion coefficient, phase diffusion factor, estimated calculated by diffusion coefficient gamma times area over delta x or y. And the third header is flux, which is the product of phase diffusion factor central difference, with 4 row headers being west, east, south. You note here that the area in each direction will be different, and displacement can also be different, and flow also can be different, designated by the subscript of every universe. Notice here, we'll select this just a bigger value. Otherwise, same diffusion. Other value in which the second western sail for the speed set this diffusion D, which is diffusion coefficient times area, the phase length, and the calculation of flux is the same. Just the same. The only difference of upwind selecting the bigger values. The discrete diffusion for the interior cell then becomes P phi P, which is the sum of all flux of K phi. The same can be said with the convection flux, is central difference, and upwind finite volume discretization, with the only difference being here diffusion coefficient, skipping the convective flux term compared to the previous calculation. Another comparison table shows that CD or central difference and upwind compares for convection diffusion problem, considering coefficient A, FW, AN, and square type of discrete equation algebraic form. A phi P is equals AE, AW, AW, AN phi W, AS, AS. Discretization. 3 types of numerical solution algorithm can be used for simulation: simple, segregated, and coupled. That the illustration show the solution flowchart. The algorithms. In simple algorithms, the following steps subsequently applied. First step is cross pressure field. Solving momentum equation of U star using T naught. Then systems assembled and integrated. Pressure correction equation for P pressure using expressions. 1 is equals to naught alpha P. This is repeated to pressures. The segregated solution algorithm, which variable is solved its own scalar equation in sequence. First, given pk, uk plus 1, next value solved for x momentum, then vk plus 1 solved from momentum, y momentum, etc. And pressure correction. Is stated. They're using simple pressure receipt. Reasons. Here, momentum and the pressure equations of all flow variables are solved in the following steps. First, the coupled system of objects for U and the P assembled. The second step, the block system solved iteratively. All builds up together. Their outer iterations may still be used for linearity. Between the simple semi-implicit method, pressure linked equation, which is abbreviation, simple S stands for semi-implicit. M is for method. We saw in the previous slide, it uses predictor corrector, which whereas pressure implicit splitting because employs simple predictor, then first corrector, then additional pressure equation using corrected inverse velocities used, and additional steps. So simple often used for steady flows and pressure implicit splitting filters or also used for unsteady flows. So this includes additional steps of time marching. Now we will proceed to boundary layer equations. The large sparse system of discretized governing equation of transverse variables. Therefore, we defined boundary conditions help balance variable mismatch. Create initial and boundary conditions consistent with the partial differential system. Equation system will be the same in the following section. The illustration shows boundary layer growth of dimensional incompressible Newtonian flow over plot with x-axis. Very normal. The velocities components are ux, y, direction, x and dxy is direction y. The pressure is dxy. The assumptions of the boundary layer is sigma much less than n, high Reynolds number, RL greater than corresponding set limit, dimensionless form. Negligible normal pressure, partial T by partial 1, 0. Negligible stepwise direction. Steady the assumptions of the boundary layer. The incompressible laminar flow with the distance isotropic. Dynamic viscosity. X mu share square u by partial x square. Marching scalars, same. Boundary layer growth, which reasonably captures boundary conditions, corresponding simplified running infinity and x and y and the equations are seen on the left hand side. Thermal boundary layer also shown with energy equation. Constant thermal properties. Negligible viscous dissipation and generation. The layer can be specified with three conditions. You can specify wall temperature using Dirichlet. Flux be specified with the Neumann method. And the third kind is convective boundary by Robin active definitions. We have already derived boundary layer in the previous slide with the partial differential equation simplification section, with the exception of thermal and energy equation. Please review the reader for details. Now you can note principal boundary layer equation at the right hand side requires yearly full Navier-Stokes simulation maintaining in boundary layer concept delta much less than L by definition. Let's see discretization, grid resolution, boundary layer grid briefly. Space near y is equal 0 for relative evolution and momentum energy coupling. The non-uniform grid in Y, the number of grids set to J, Jacobian, used maintaining local stability by empowering decay algorithm involving characteristic eigenvalues. First and second derivatives in the boundary layer thickness, the grid approximated using central difference as shown. Streamwise derivative is approximated with backward difference. The boundary continuity equation, we can compute the boundary layer velocities by integrating y from the wall and integrating it from where is equal 0. All shear stress and diffusion coefficients determine solving momentum equation. Velocity profile integrated above uxy and ux. Calculated solving energy equation and the heat transfer coefficient determined using expression of Nusselt number. Solution. Energy equation for temperature profile determination. Analysis involving temperature dependent density. Using approximation can be used to update temperature, buoyancy, momentum. Equation repeated until convergence. Heat transfer through side wall determined using conjugated transfer. All boundaries. The interface energy determined using Gaussian diffusion. So this brings us to the end of the session we have been discussing so far. The new topic I want to introduce you is introduction. All the previous topics are the exception of the general basic segregation. Is with specialized technique flow speed U bar, where U is categorized as mean turbulence, certain set of limits, and excessive, which is U, that's right hand side, by averaging known as Reynolds average Navier-Stokes model. Five turbulence models should be used, and their corresponding application suitabilities are, since this is introduction, the first one is Reynolds stress model. This solves 7 sets of equations linked isotropic and identical turbulence in different directions well. The second model is the standard Reynolds Stokes equation. Epsilon. On the other hand, assumes isotropic viscosity the same in all directions and is suitable for free turbulent flows, free shear flows, and high Reynolds number. Omega helps to model swirling flows with a strong curvature, anisotropy, all bound with adverse pressure gradients. RGD simulation is used to model unsteady, that is scale separation. Example, flow over cylinder is a resolved large PDEs using subgrid scales. Such a PDE simulation resolve large scales, model only small scales using blends of average Navier-Stokes equation, which is the first method. So resource intensive. Here was only this large simulation in separated regions. See you in the next session. Thank you for attention.